And chemical kinetics is this. It is the speed at which a reaction takes place, okay? And when you do chemical kinetics, you can actually view the change of the reactants in a step-by-step mechanism, okay? And you'll do a lot of this actually in organic chemistry, step-by-step mechanisms of reactions. You're not going to do it much here, but chemical kinetics is really studying how fast the reaction goes, okay? There are a few things that can affect reaction rates, okay? One of those things is the physical state of the reactants. Things that are solids don't react as fast as things that are like liquids, for example, because you have to have things mix, right? And solids don't mix well with other solids, right? They just kind of hit each other. Whereas liquids can mix together easily, right? And they can do a reaction. Reaction concentration. So we talked about this before with Le Chatelier's principle. Remember that? Right? More reactants means what? More products. Remember that? Wait, I don't know if I told you that. Did I tell you that? Oh, that was a different class. I'm sorry. Yes. So the more reactants you put into the more reactants you put into a reaction, the the faster it goes to become products. Reaction temperature, of course, I've told you this before too. I know I've said this in here, right? If you heat up a reaction, it makes it go faster because you're making the collisions between the molecules faster, right? Because a reaction really is just a molecule colliding with another molecule. And then the presence of a catalyst, okay? And a catalyst is just something you use, right, to make the reaction go faster. But the cool thing about a catalyst is that you don't actually use it up. It stays the same afterwards, right? So the best example of that is in the hydrogenation of fats. So someone was asking me a little while back about saturated fats and unsaturated fats. Remember that? Well, sometimes you can take a fat that is unsaturated, which means it has some double bonds in it, and you can use platinum with it and make it all hydrogenated, which I'll tell you more about that later, but it becomes basically saturated, right? But platinum, you're eating your butter and there's no platinum in your butter, I promise, right? And the reason why is because you can put that platinum there, right? It does the reaction, and you take the platinum out, and you're eating your butter, right? It's good. And the platinum stays the same, okay? So that's what a catalyst is, right? So let's go through a couple of these real quick, all right? I already talked about this a second ago. Physical state of the reactants. The more readily reactants collide, the more rapidly they react, right? So homogeneous reactions, gases and liquids are often faster, and solids are slower, like I just said, because you throw two solids together, like you throw this podium against this table here, it stays the same, right? It doesn't react. So, yeah. And then reaction concentrations, right? Increasing the reactant concentration will also increase the reaction rate. It will make it go faster, right? It will make it go faster. The reason why is because there's more molecules, and more molecules means more collisions, right? So here we have a picture of steel wool heated in air, right? Where air is only about 20% of the atmosphere, right? Because most of it is nitrogen, and it burns fine. But when you put it inside of a flask and you pump it with 100% oxygen, what happens? It totally burns, right? It blows up, okay? So it makes the reaction go faster. Whew. Next, right? Temperature. I already said this before too. Temperature will also increase the reaction rate. And temperature, when it increases the reaction rate, is because it makes more collisions, right? And then I talked about catalysts. And this is the last slide for today, okay? Catalysts affect the rate, right? Catalysts affect the rate, making it faster without being involved in the overall reaction, okay? That's the big deal right there. You can put a catalyst into the reaction, it will make the reaction faster. You can take it back out, and the catalyst is still the same. That's the thing to remember about that, okay? Catalysts affect the kinds of collisions, changing the mechanisms, the pathway of the reaction, and the catalysts are critical in many biological systems. So whenever I'm talking about enzymes, that's what I'm talking about. They're biological catalysts. So your first question is this: which of the following affects reaction rates? Which of the following affects reaction rates? All right, let's see how people are doing. Got one response so far. Whoever that was, they did it right. Good job. So we have 10 people in here. Oh, I wonder where Kimberly and Aubrey are. I just talked to Aubrey earlier. Weird. 7, 8 people. 2 more people, please. This question should actually be familiar because we did this question last week, but I'm going through the PowerPoint again. So, still waiting for 2 people. Still waiting for 2 people. Unless I miscounted. I did miscount. There's only 9 of you in here. There we go. 1 person. So, as I alluded to before, good job. Everyone got that right. All those are types of catalysts, right? All these are not type of catalysts. Sorry. All these are things that can affect the reaction rate. Okay. So the next few slides are going to be just going through each one of those individually. I pretty much did it already on that first slide, but just as a quick reminder, because I'm going to ask you questions about this, right? The more readily a reactant collides, the more rapidly they react. Just like I was talking about before with things that are solid, you throw 2 bookcases together, they're not going to react to make something new, right? But if you have 2 liquids or gases and they collide with each other, the molecules actually collide with each other, then they will react more rapidly, right? Homogeneous reactions, all gases, liquids are often faster. I just said that, right? And heterogeneous reactions involve solids are slower, right? Faster. The faster these reactions occur, if the surface area is increased, and a fine powder will react more than a pellet or a tablet, right? So again, the reason why it's a fine powder is because if there's more surface area around the actual hard solid material, there's more collisions that can occur that can actually have the reaction. So the thing to take home from this is that things are liquids and solids, liquids and gases. They often react much faster than we have a solid and a liquid. So we also have reaction concentrations right here. If you look at this picture, which I showed you last week too already, this is just some steel wool right there on a Bunsen burner, right? And it glows red hot when you put it on a Bunsen burner. But when you put that same steel wool inside of a beaker or a flask rather, and you pump it full of oxygen, it almost explodes, right? Because the reaction is much faster when the concentration of oxygen is much higher, right? Because remember, out in the atmosphere, there's only like 20%, oxygen, 25% oxygen. But inside this flask, you can pump it full of oxygen, and then you'll have a little bit of an explosion happen because it reacts much faster. I wanted to do that in class, but they wouldn't let me. They said it was too dangerous. So it's too bad. So another thing, again, I said this already before, the temperature also increases reaction rates because you get more collisions, right? Increasing the number of collisions between the molecules. That increases reaction rates because you heat something up and the molecules just bounce around much faster. And last, and certainly not the least, the presence of catalysts, right? A catalyst will affect, this is the definition that you need to know, the catalyst will affect the rate without being in the overall balanced equation, which means you can throw in a catalyst and then it'll do its thing to make the reaction faster, and then you can pull it back out again. Nothing changes with the balanced equation, okay? How do you do it is by changing the mechanism of the actual reaction, and then catalysts are critical in many biological reactions, and they absolutely are. If you didn't have any biological catalysts like enzymes, you'd be dead. You would be absolutely dead, okay? Next question. Which of the following is not true about a catalyst? Catalysts affect rate by being a part of the overall balance equation. Catalysts affect the kind of collision based on changing the mechanism. Catalysts are critical in many biological reactions. Or D, all the above are true. All right. Read the question carefully. Read the question carefully and read the answers carefully. Read the question carefully. It's okay if you got it wrong. If you know you got it wrong just now, then I'm fine with that. I might laugh at you later when I'm going through the attendance, but but it's fine. I'm glad you realized that you made a mistake. Right? Read the question very carefully. All right, we got 8 responses. I need one more. I'm, I'm holding on. Cool. All right, so we literally had half and half here, which is fine. It's still Monday. It's early. Well, to me, it's early because I woke up like 10 minutes ago, but maybe you guys woke up earlier than I did. The vast majority of you said A, right? Well, there can't be half and half because there's an odd number of people today, but not the vast majority, but the majority. There we go. Maybe it's called the plurality. The plurality of you, right, did answer the correct answer there. It is answer A because remember the definition of, and this is the definition you need to know for an exam, right, is that catalysts affect the rate by not being a part of the overall reaction, okay, by not being a part of the overall reaction. So that's why A is not true because that says it's being a part of it. It's supposed to be not a part of it, okay? So moving forward, talking about reaction rates, the rate is a change in concentration over a period of time. And you actually saw this when you did the experiment last Wednesday, when you put the stuff into the Spec 20 and you saw the numbers going down. Remember that? Right? That was actually a change in the concentration of crystal violet. Okay? Because it reacted with the hydrogen peroxide, the crystal violet was changing to something else, and that's why the numbers were going down. Does that make sense? Right? So we generally use this equation here where we have the change, this triangle right here, which is a delta, is a change, and then the brackets right here are concentration, right? And then divided by the change in time, okay? So, just to say one more time, just to be reiterating here, the rate is equal to the change in the concentrations of a reactant or the product or anything over the change in time. Okay, so delta means change, brackets means concentration, T's mean time, right? So the average rate is measured in the average rate, the instantaneous rate, or the initial rate. Those are the 3 types that we measure, okay? The instantaneous rate, the average rate, and the initial rate. So let's apply this then to a reaction. Okay, so let's apply this to a reaction. So we have here this molecule, I don't know what this is, 4, so that would be butane, right? So yeah, maybe this is called butane chloride, or chlorobutane, right? Chlorobutane, right here, the C4H9Cl. That's not so important what the name of it is, right? But you're going to be combining that in a reaction with water, and what you get out of it is butanol. Wait, that's not even butanol. Is that butanol? Yes, that is butanol. Yeah, okay. You'll get butanol and hydrochloric acid, right? It's almost like this is what they do, the reaction that they use to actually make hydrochloric acid. So that's pretty cool, right? So you get butanol and hydrochloric acid, right? Both of them are AQ. What does that mean? Exactly, aqueous. They're in solution, right? And so the rate of the reaction is measured using the concentration of change of reactant over the product over or a product over time. So here in this example, we're going to use one reactant here, right? That reactant will be chlorobutane or butane chloride, chlorobutane, whatever, same thing, right? And so since we're looking at the concentration of the chlorobutane, we're going to put the chlorobutane's formula inside of the concentration brackets, right? And so the equation then now is the rate, right? The rate equals negative change in chlorobutane over change in time. Can anyone tell me why we have a negative there instead of just regular old change? Well, if you think about it, chlorobutane is being changed into butanol, right? So we're losing chlorobutane as time passes. Does that make sense? And since we're losing chlorobutane as time passes, that's why it's a negative number, right? So if we were to put a product there instead, like hydrochloric acid or something there, or butanol there instead, it would be what? A positive number, because we're getting more of those. Does that make sense? Right? So, yes, ma'am. Yeah. Yes. Yes, that is a division sign right there. Yep. But yeah, so if you were to put the products, one of the products in the concentration brackets, it would be positive, right? Because you're making products. But if you put one of the reactants into the concentration brackets, it would be negative because you're losing reactants as time passes. Does that make sense? So that's why it's negative right there, okay? That'll come up later. All right, I'll give you a chance to write that down. And while you're writing that down, here's your next question. Keeping you involved today. I keep you involved every day, don't I? You guys should be excited. I'll be the one teaching your lab this week, right? Because Miss Dickens was going to cover for me if I was gone. So, and it's going to be an easy one. It's going to be all on computer, so you don't have to, get dressed up for lab that day. You wear shorts and tank tops or whatever it is you crazy kids wear these days. I was going to say you don't have to wear pants to class, but that sounded weird, so I refrained from saying that. Except I just said it just now, so. All right, let's see how people did on that question. Everybody's responded. Good job. Woohoo! Everybody got that one right. The delta means the change, right? Which is A. Good job. Yes, ma'am. Seconds. Yes, ma'am. Some reactions take longer than other reactions, though, so it could be milliseconds or shorter. But generally, when we're talking about like using the SI system, right, time is always going to be in seconds. All right, so I want to show you the rate of this reaction right here. It's kind of interesting here. If I can get to that slide, there we go. All right. So what happened? Okay. So here's the reaction data for butanol chloride. No, what did I call this? Chlorobutane with water, right? So here we have time. It's in seconds, right? And you have 0 seconds here. You're ending with 10,000 seconds there, right? Here on this, at the top here, we have the concentration of chlorobutane. And then over here, we have the rate of this reaction. And notice that the rate of this reaction, the units of this rate of reaction is what? It's not meters per second, is it? It's like molarity, right? Molar per second, right? So that's the change in concentration over time, right? Big M is always molarity. And what I want you to notice here is that as time passes, right, the concentration of chlorobutane gets smaller, right? Here at 50 seconds, it's 0.905. At 100 seconds, it's 0.802, 820. At 150 seconds, it's 0.074, and so on. As you see, it is actually going down because over time, you're going to change all of that chlorobutane into what? Butanol, right? And hydrochloric acid. The other thing to notice here too is that notice how at the very beginning of the reaction, the rate is faster, but then by the time you get to the end of the reaction, the rate is like a fourth of it, right? So two things to notice in this chart here, okay? As time passes, the concentration of chlorobutane decreases, and as time passes, the average rate of the reaction decreases, right? Those are two things to notice there in this chart. I told everybody last week that I'm like totally winging this and I have no idea what I'm talking about. And I literally just I don't know the stuff like ahead of time. I just like look at the slide and tell you what I see. So so otherwise I'd have like notes and I have like a script, and everything. But no. I'm winging it just like you guys are. So it makes you feel reassured, doesn't it? Okay, so let's talk about graphing the data from the previous slide. When we graph the data from the previous slide, we can actually determine some very interesting values, one of which is called the instantaneous rate. The instantaneous rate is basically the rate of reaction at any given point in time. Okay. At time zero, though, we call it the initial rate, and it's important and special to us because at time zero, generally the rate is at its fastest because as you can see from over this graph, you can see on this graph, as the reaction progresses, the reaction rate actually slows down, right? The reaction rate decreases. So if a chemist wanted to be able to see what the reaction's rate actually is, he or she wants to see it at its fastest, they'd want to get the instantaneous rate at the at point zero, right? Right when we first start the reaction, okay? And so we can actually very easily figure out what the instantaneous rate is at point zero, or the initial rate, right? Right here on this graph, it even tells you that the instantaneous rate at time at any given time is equal to the slope of the tangent at that time, right? Equal to the slope of the tangent at that time, right? So let's use that to figure out the initial rate or the instantaneous rate at zero uh, here, okay? So here is the rate, here's zero right here, okay? And here's the concentration of the reactants at time zero, okay? So we want to be able to figure out the instantaneous rate or the initial rate right there at that point, right there that I'm putting the arrow on, okay? And the way we do that, based on the statement right here that I just underlined, the way we do that is by taking the slope of the tangent to the dot or the data point at time zero and concentration 0.1, okay? So, bring over a ruler, and I have one on, oops, didn't mean to change the screen there. Let me go back. Go back. There we go. So I have a ruler here, and I can put the ruler on top of my screen, and then I can draw a very straight line that will represent the tangent of that line. Okay, the tangent of the line at that point, right? Okay, and so when I do that, what I need to find now then is the slope of this line. Okay, the slope of that line, because the slope of that line equals the instantaneous rate, right, at that point. Okay, and really you could actually go up and down the line of the data, right? This line that's made by the data here, pick any one of those points on that line, that curved line, right? As long as you use the slope of the tangent of that point on that line, you can use any of those lines, and you should come up with a reasonable number, right? But since we want the slope at since we want the slope at the time zero or the initial rate, right? We're going to use this line and this slope right here, and at that point. Okay. So if you recall back when we were talking about graphing in very early on the semester, right? The slope of a line is m equals the change in y over the change in x, right? And then also, if you recall, back, maybe 2 or 3 slides ago, I can't remember, right? The rate actually equals the negative change in the concentration of the reactants, right? So in this case, it's the the chlorobutane. So that's C4H9Cl, all divided by the change in time. Okay, all divided by the change in time. I want you to also notice here that this term is negative right here. It's definitely negative, and the reason why it's negative is because we're losing reactants over time, right? If you were talking about the products being made, like the butanol or the HCl, then it would be a positive. But we're looking for the instantaneous rate of
the reaction as the chlorobutane is being lost, right? Is being converted over to something else. Okay, so quite simply then, we'll try to figure out to get this rate, right? We need the change in y over the change in x. So in this case, y is the change in concentration, right? So I will move over to the left over here where I have a little bit of room, and I can write the equation out as the rate equals, right, the negative, and I'll go ahead and put the divide sign there so I know what's above and what's below. And we're going to just choose this line right here for the y, right there, and we'll get the slope at that tangent line right there, right, that change right there. So our initial here is 0.1, and our final here is 0.06 molar, right? So on the top, we'll put 0.6, oops, 0.06, right, minus zero point 0.1, right? And then at the bottom, it's a change in time, right? It's a change in time. So there, we'll estimate here a little bit. This tangent line comes over here a little bit, right here, and we'll take it all the way down to the x-axis. And I'm thinking that is about 210 seconds. So the final first, which is 210 minus 0 seconds, because we were at time 0 at the beginning, right? And all we have to do now is do this multiplication here, or sorry, this division here, right? And we can solve for the instantaneous rate at time 0, right? And I'll take this down here so I can write it out more clearly. We get the answer to be then an instantaneous rate of 1.9 times 10 to the negative 4 molar per second, okay? By the way, that is the unit molar per second, okay? And so the interesting thing about that is that we ended up with a positive sign here, even though we had a negative sign here in the equation, right? You just got to remember your order of operations here. And so since this top term right here actually becomes negative, a negative times a negative makes a positive, and that's why we have a positive rate. That being said, though, the graph does show that the rate is slowing down, right, and going in downward direction as as the reaction progresses. So the other interesting thing to notice too is that when we just did this calculation right here and got this particular answer, and I don't know why I didn't draw a square around the unit 2 because it goes with it, right? We can go back to the data from the previous slide and see if we match up, right? And if you notice right here on the slide, on the previous slide, right, here's time 0 right there, and look what the rate was. It's exactly what we calculated, 1.9 times 10 to the negative 4, right? Molars per second. Never forget the units, right? So that's how we do that.
Okay, so I actually talked about this a second ago, okay, but we'll rehash it here again because it's important. Okay, as you said, rates are followed using a reactant or a product, right? So does this product give the same rate? Does this give the same rate for each reactant and product? Well, the rate is actually dependent on stoichiometry. Okay, it's dependent on stoichiometry, and if we use I keep on forgetting its name, chlorobutane, and compared to the production of butanol, right? The thing that would change is the sign, right? And I said this a second ago, right? We have a decrease in chlorobutane, and that's why the sign is negative, right? But when we have an increase in butanol, then the sign is positive, right? The sign is positive because as the reaction increases, butanol's concentration goes up, so it's positive. But as the reaction progresses, the concentration of chlorobutane goes down, and that's why one of them is negative. This is always the reactant, and the one that's a product, right, is always going to be positive, right? So I could put here what? I could also change that to say HCl, and it would still be the same, right? Because that HCl was a product too. Or I could change this one to say water. That was a reactant. Does that make sense? Right? Okay, good stuff. Good stuff. Yes, absolutely. Absolutely. And I'm about to elaborate elaborate on this statement here. Rate is dependent on stoichiometry in just 1 second. Letting people get a chance to write down what I just said. Sorry, this is like my some of my favorite stuff. So, it really is some of my favorite stuff. But luckily, there's a video. Luckily, I'm recording, right? Luckily, I'm recording, so you can go through and listen to it again. Okay. Yes, when you put a reactant into the rate equation, it's always going to be negative. But when you put a product into the rate equation, it will always be positive. Yeah. I mean, I usually get really excited and go fast on other things too, but this is some of my favorite stuff. The rate equation, the rate equation, and it's called the rate equation because the rate equals something. That's why it's called the rate equation. Yes, ma'am. You have a question, don't you? Yes, it was. That was literally a quiz question on the lab. That was a quiz question on the lab. I'm so glad you noticed. All right. So I'm going to go on a little bit here.
So I was just saying how the rate is dependent on stoichiometry, right? And what did I mean by that? Well, what I mean by that is the fact that what if you don't have a one-to-one ratio, right? In our previous example, we were doing the chlorobutane with water, and our results were a, uh, butanol and a hydrochloric acid, right? But when we wrote that reaction out, the balanced chemical equation was a one-to-one ratio for all the reactants and all the products, right? So what do we do when we have a reaction when it's not a one-to-one ratio like this one and this one here, where we have uh, ozone decomposing into oxygen, right? And the ratio is actually 2 to 3, right? 2 to 3. What do we do with that? Well, there is this general rate equation, right? And it's based on this general equation of a chemical reaction, where if you have little a is a coefficient to big A, which is a reactant, right? Plus little b is a coefficient to big B, the reactant. That turns into little c, big C product, plus little d, big D product, right? And knowing that that's just a general chemical equation for any kind of reaction, right? We then know that we can do this, right? We can make a general rate equation like this one right here. So the rate equals, right? For the reactants, it's always going to be negative. So negative 1 over little a times the change in the concentration of big A over the change in time. And that also equals the negative 1 over little b times the change in concentration of big B, right, divided by the change in time, right? You can do that on the product side as well. The rate equals, since it's a product this time, though, it's not going to be negative, right? So it's going to be 1 over little c times the change in concentration of big C, the product, right, divided by the change in time. And that equals 1 over little d, and again it's positive this time because it's a product, times the change in the concentration of big D over the change in D. I mean, the change in T, or time, right? So as you can see here, here's our big A, right? And here's our, what represents big A in this equation is the O3, or the ozone, right? And in this particular equation, we only have one reactant, so we don't even have to worry about uh, the B term, okay? And then for this reaction here, C, little c, right, is 3, and big C is O2, or oxygen, right? So now we have all we need to write out the rate equation, right? Well, we have all we need to do, right? Because 2 again is little a right there. Ozone is big A right there, the concentration big A, right? We go ahead and not worry about, whoops, I'm sorry. We go ahead and not worry about the B term, right? Because we don't have a second reactant. And then the same thing is also true over here with the products. We do have a single product here, which is oxygen, right? But we don't really have a second product, so we can just, not worry about that second product either, okay? And so what happens here is that since this is the 2 for little a, and little a is now down here in that equation, right? This is what you get right here, negative 1/2, right? The 2 becomes the denominator, right? Because the little a became the denominator in this rate equation that we have here, this general rate equation, okay? And then as for the 3 here, it became the denominator down here in the products of the rate equation, right? Because if you look over here, little c is under 1 right there, right? And so that's how we write our rate equation, okay? These two terms right here can actually be all combined into one. I just split them up there because I ran out of room. But you can write it as the rate equals the negative of 1 over little a times the concentration, or the change in the concentration of big A, right, divided by little t, which is time. And then that equals negative 1 over B times the change in concentration of B over the change in time, right? And remember that both of these right here are reactants, and that's why they're negative. But then we come over here to the products now, and it's positive, so now you can just write equals 1 over little c times the change in big C's concentration over the change in time. And then the same thing is then also true of D, 1 over little d times the change in concentration in big D all over the change in time, like so, right? And so that's how we figure out how we write the equation with the coefficients, right? Because remember, when I'm talking about stoichiometry, I'm talking about the coefficients that are in front of each of the reactants or products, right? And whenever the stoichiometry is not 1 to 1 or the coefficients are not 1 to 1, this is what we have to use right here to figure out what our rate equation is going to be, right? Interesting stuff.
Here is your next question. Don't worry, it's an easy one. What is the mathematical rate dependent on? Temperature, concentration, stoichiometry, or all the above? This is such a good time. I hope you guys are enjoying this just like I am. I really hope you guys are enjoying this like I am. I mean, I'd venture to say this is one of my best lectures ever because I'm using the board, I'm using the PowerPoint. It's like hybrid type of style. It's a great time. I'm sure you're all thinking in your heads, well, I'm glad he's having a good time. At least somebody in the room is having a good time. It's not that bad, I promise. Especially when you listen to the video over and over and over again, like at least 20 times. It's great. If anything, it'll help you fall asleep at night. Oh, that Dr. No talking math. It makes me so tired. All right, so looking at the answers, Good job. The vast majority of you got that one right there. The answer is, in fact, stoichiometry, right? Stoichiometry is what we depend the mathematical rate on because stoichiometry is what? The coefficients, right? And those coefficients literally go straight into um, the the rate equation, right? They go straight into the rate equation. And there, I don't know if you remember me saying this a second ago. I put a big T there a second ago. Remember? It's like, wait, it can't be big T. The reason why is because big T stands for what? Temperature, not time, right? Little t is time, big T is temperature. And so that's why all these have the change in little t's. Okay? All right then. We're doing so well. We're making such, well, we're not making super good time, but that's all right. I plan on spending the next three days on this, so it's all good. Oh, I forgot to change it back over again. Okay. So determining the concentration effect on the rate. How do we determine what effect the concentration of each reactant has on the rate, right? So a second ago, we were talking about the coefficients having the effect. Now we're actually going to talk about the concentrations having an effect, okay? We keep every concentration constant except for one reactant to see what happens to the rate. Then we change to a different reactant, and we'll do this until we have seen how each reactant affects the rate. And I'm going to show you what that means in just a second. Yeah, no problem. Yeah, no problem. No problemo. I am here to serve you guys. You pay me very well to sit here and talk. So I serve you guys.
I went to the bookstore today
to
to
Uh-huh.
buy a charger.
Uh-huh.
It was $25, and then
Oh my God. Go to Amazon and buy it for like $1.
well, I needed it like right now. And then I went. It wasn't the right charger. I
Of course
tried
not.
it to try and make it work, but it wasn't the right charger. So I went to the Dollar Tree up there,
Yeah.
and it was only $6 there.
Well, for one thing, I think that's weird that Dollar Tree is selling things for more than $1. But number two, it is still cheaper than buying it at the bookstore.
Like I was shook.
I was too when I went to buy my very first Wesleyan T-shirt, and it was like $40. I'm like, holy crap, really?
Wait, it was $20.
Yeah, right.
A charger is half the price of a sweatshirt. That is ridiculous, y'all. That is ridiculous.
At least you think, at least like there's like licensing agreements, and that's why it makes the sweatshirts more expensive. But like the charger though, that's like generic from China. That should be like $1. Oh, I should go get some. Yeah, the one it's right across from President Slaybox's office. Dang.
That was 2 weeks ago.
Must be the wrong season for getting certain things, I guess.
If you shop online too,
It's cheaper.
it's cheaper.
Okay, so we're actually getting close to the end of class. No. I was gonna say that this stuff is a little complicated. So, do you want to go over anything, talk about anything before you go into discussion to do the problems, or do you want to continue until the time ends? We have like 7 minutes. To what? What questions? Yeah, I'm gonna go over that. I can if you want me to.
Don't you think, are we doing that in discussion? What you're about to?
Quite possibly. I don't remember. Quite possibly. So I better go over it.
Our homework is due tonight, right?
Which homework?
Homework 6.
Yes, it is due tonight. Everything is always due. Yeah, assignment 6.
Everything is always due what?
Everything's always due at the end of the day of the next class period that it was assigned.
Okay.
That way you have time to ask me questions about it before it's due. Right? Okay, so just to I guess I'll try to finish this part. That way you're not like lost in discussion later, okay? As I was saying in this previous slide right here, right? What we do to figure out what the concentration has on the rate, how we figure that out is that we change one of the reactants of the reaction to see how it affects the rate, and then we change the other of the reactants to see how it affects the rate. And the way we do that is by doing this, okay? So now I have a reaction, right, in which I'm combining, right, ammonia with nitrite, okay? And so for experiments 1 through 3, right here, experiment number 1 through 3, 1 through 3, what's happening here is that I'm doubling the concentration of ammonia, right? But I'm keeping the concentration of nitrite the same, okay? To see how that affects the rate of the reaction. And then for experiments 4 through 6, right? 4 through 6, I'm keeping the concentration of ammonia the same, but then I double the concentration of the nitrite. Does that make sense so far? Right? And I want you to see what's going on here. When I double the concentration of ammonia and not the nitrite, right? The rate actually doubles, right? I start out with around 5, I get to around 10, and I get to around 20, right? The rate doubles. But then when I change over to where I'm keeping ammonia the same and doubling the concentration of nitrite, the same thing happens again. The rate starts out at 10, so around 10, doubles to 20, around 20, and then doubles again to 40, right? So whether I double the concentration of nitrite or double the concentration of ammonia, right, the rate doubles, right? So the thing you can say is this. When I double the concentration of the reactants, I double the rate of the reaction. Does that make sense? Okay, that's like the general thing you can say, which is actually on the next slide. I just wanted to say it ahead of time. Okay, so for experiments 1 through 3, right, the concentration of nitrite stayed the same. So any of the changes in the reaction is actually because of the change in ammonia. Reaction 1 through 3 was the one where I doubled the concentration of ammonia, right? Every time. So you can say, for example, this here, where the rate 1 of ammonia, right, the rate of the second reaction, right here, right? Remember there are 1 through 3. I wish this was on the same slide, right? So remember it's reactions 1 through 3, right? 1 through 3, okay? So here on this equation, what it is that this is the rate from reaction 2, and this is the rate from reaction 1, right? Which equals the concentration of ammonia in reaction 1 times divided by the concentration in reaction 1. I'm sorry, that's reaction 2. Let me say that one more time. Rate of reaction 2 over rate in reaction 1 equals concentration of ammonia in reaction 2 over the concentration in reaction 1. Okay, does that make sense? And when you take those numbers from over here, from reaction 1 and 2, right, and you plug them in, what you get is 2 equals 2, right? The concentration, this number here is 2, right? And then for the rates, it's also 2. So 2 equals 2, right? And so what that means is that the order is 1. The reaction order is 1, okay? Now you may have noticed that there's an X there. We'll talk about that later. But this X here means that, say instead of going reaction order is 1, right? Usually that 1 goes right there where the X is. But say instead of the rate doubling, it quadruples every time, right? Then instead of this order being 1, it actually would be what? 2, because 2 times 2 is quadrupling, is 4. Does that make sense? Right? So since you see that the rate divided by the rate here for the first and second reaction equals 2, and the concentration of ammonia divided by the concentration of ammonia is also 2, the order of the reaction is order 1, right? Does that make sense? I know this is crazy stuff. So this is your next question right here. With respect to ammonia, as the reactant, oh, I forgot to put the word double there. As the reactant doubles, right, insert doubles in there. As the reactant doubles, what happens to the rate? I haven't actually combined everybody yet, but it's pretty close actually. Sorry, somehow I messed up that question and forgot to put in. With respect to concentration, As the reactant's concentration doubles, what happens to the rate? Oh, I did say that at the bottom there. Yeah, what happens to the rate when the concentration doubles of ammonia? Okay. Okay. Oh my gosh, good job, everyone. Good job. Oh, you haven't put in yours yet? Okay. No problem. All right. Good job. Again, the vast majority of you got this correct because I said it like 5 times, right? For this reaction with ammonia and nitrite, when we doubled the concentration of ammonia, we also doubled the rate, right? But as you can see from my uh, options, right? You can see from my options, you can do reactions where the rate stays the same, or it can triple, or it can quadruple, right? Those are possible, and you'll see those later, okay? Let's do the same thing again now, but instead of a second ago we saw the numbers for changing ammonia. Now let's look at the numbers for changing nitrite, doubling nitrite. Same thing again here, right? Here, ammonia stays constant, so any change is due to only the nitrite concentration. And here, when we put the rate of nitrite over the rate of nitrite divided by the concentration of nitrite and the concentration of nitrite from reactions 3 and 4, we get the same thing again, where it's 2 equals 2. You divide this by that, it's 2. You divide that by that, it's also 2. So that is also order 1, right? So as the concentration of nitrite doubles, what else doubles? The rate doubles, right? So you should be hearing like a pattern now, right? Whenever the rate doubles, because the concentration doubles, the order is 1, right? Whenever the concentration doubles and the rate is quadruple, the order is 2. Make sense? Right? And you'll see more examples of that in a second. Okay? All right. This is going to be your last question for today, because you need to go over to the other classroom. What is the order of this reaction with respect to nitrite? This stuff is so fun. Like, once you really get it, it's so fun. We've got 7 people responded already. Still waiting for 2 more. That's good enough. 8 people responded. Good job. Everyone got that one right. In fact, when you double the concentration of nitrite, you get double the rate. Say we're talking about this reaction here, right? The one between ammonia and nitrite, if you recall, right? In the first 3 reactions, we changed the concentration of one of the reactants, in this case ammonia, and we saw that as we doubled the concentration of ammonia here from 0.01 to 0.2 to 0.4, the rate also doubled here. See, we have on the order of 5, and then 10, and then 20, right? And then on the other side of the equation, not the other side of the equation, sorry, in the last 3 reactions, this time we kept the ammonia concentration. We kept the ammonia concentration constant, and now we doubled the nitrite concentration, right? So here we're going from 0.0202 to 0.0404 to 0.0808, And as we did that, we saw the rate double as well, right? From 10 to 20 to 40, right? We see that trend right there, okay? And so when we take a look at the whole thing, right? Experiments 1 through 3, how it affects the rate, how ammonia affects the rate, the concentration of ammonia affects the rate, and experiments 4 through 6, how it affects the rate for nitrate concentration, right? We find out then that the rate law is actually uh, 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 first order for both of them, right? Because remember what I said on Monday, when you have a reaction, uh, that is when you double the concentration and the rate doubles, that's called a first order reaction, right? And so we know then that remember that this equation right here actually comes from this rate law, general rate law equation here. Rate equals K concentration of A, and then X there, and then B, and Y there, right? So in this case, the ammonia is the A, and the nitrite is the B, right? Is the B, okay? And then our order of reaction is the X and the Y, right? Is the X and the Y. And since when we looked at the data, right? When we looked at the data on the previous slide, we saw that doubling the concentration of ammonia doubles the reaction rate, and then doubling the concentration of nitrite doubles the reaction rate too, right? That's called a first order reaction, right? And since the X and the Y are the orders of the reaction, by the way, RXN is an abbreviation for reaction, right? Then we know that both X equals 1 and Y equals 1 for first order, right? For first order. And so this Y goes here, this X goes up here, and then when you look at the actual rate law, you don't see any numbers there, right? Because when there's not a number there for the exponent, what do you assume it is? 1, right? So that's a first order reaction. And just as a quick review, right, from last Monday, if you double the concentration and it quadruples the rate, that's a second order reaction, right? But for this one, we have a first order reaction, okay? So looking at the same data again, right? Looking at the same data again, let's talk a little bit more about the rate law, okay? When we look at this reaction overall, we knew already that just from the previous slide, right, that the ammonia concentration or the rate with respect to the ammonia concentration is order 1, and the rate with respect to the nitrite concentration is also order 1, right? So a question might be asked in which what happens when you make it an overall, like the entire? What is the overall rate reaction order, right? Well, it's quite easy. All you do is you add the first one to the second one. And since both of these are 1, 1 plus 1 equals 2, right? So the overall reaction order here is what? Order 2, or second order, right? Does that make sense? Right? Anybody lost? Everybody got that so far? Right? Huh? Who said no? What's wrong? Yeah. So remember from the previous slide, I said that the order of the reaction with respect to ammonia was 1, right? There was a 1 right there. Imagine that there's a 1 up here. And then also there's a 1 here too, because the reaction with respect to nitrite is also 1, right? Because when you either double the concentration of the nitrite or double the concentration of the ammonia, right? You get a double in the rate of the reaction, right? So that's where those 1s come from. But then the question is then what is the order, right? What is the overall reaction order, right? The overall reaction order, this line right here. Well, you find the overall reaction order by just adding the 1 plus the 1, and that's how you get 2. And so the overall reaction order is second order. Does that make sense?
I'm trying to understand what the reaction order is. Like,
It tells you, the reaction order tells you that one thing, right? It tells you whether or not doubling concentration quadruples the rate, or doubling concentration doubles the rate, right? So in this particular reaction right here, when you double the concentration of either one of the reactants, it doubles the rate. So that's why it's order 1, right? But if you double the concentration and it quadruples the rate, that's order 2. Does that make sense?
But then the overall is
The combination of both of them together. Both, yeah, the overall is 2 because you're adding the rate from the one reactant to the rate of the other reactant. And the reason why it's confusing to you is because you didn't see us go through on Monday the entire, going each one individually. You know what I mean?
yeah. So we need to watch it.
Yeah. What's up?
What if it's on NH2?
Say again?
What if on NH2 instead of
Yeah, then the overall reaction order would be 3. Yeah. That's rare, but it's possible.
Are they usually the same?
No, it depends on. So that's the one thing that we talked about on Monday. It's based on the reaction stoichiometry, right? What the coefficients are in front of each of the reactants, right? And so when we did this reaction, it was a 1-to-1 for everything in there, right? All right, everybody got it? Should I move on? Right? We're just rehashing what we did on Monday right now. So if you were here, right? So here we go. Here's your first question. Yeah, there's such thing as a zeroth order, right? Zeroth order, we'll get to that later today, but zeroth order is when you double the reaction rate and then nothing happens. No change in the I forgot already. No change in the rate. No, not necessarily. Don't think about it like in terms of like kinetics is kind of its own mathematical thing. So unless I say something, because you're going to confuse neutral with like making like a neutral reaction, like neutralizing reaction. Yeah. It's not the same thing. Okay. Yeah, it's not the same thing. All right, so let's see here. We just talked about the reaction order for the overall reaction order for the I lost my train of thought again. The overall reaction order for the ammonia and nitrite reaction. So let's see how people are answering.
So that's what it's talking about?
Yeah, the previous slide, right?
Hold on, Sunny.
Oh, I'm still looking for the actual question. Here's overall reaction order. How many people are in here today? Wow, is everybody here today? No. Except for Naraya, which she told me she wasn't going to be here. So, 10, 6, 11. There's 11 of you today. We're waiting for one person. Une person. Okay, there we go. All right, so let's see how everybody answered. This is one of those questions where I literally said it right before the question and what the answer was. And I'm glad to see that the vast majority of you got that correct. The reaction order, overall reaction order for the reaction we just talked about is C, second order, right? And the reason why it's second order is because when you look at this guy right here, this previous slide right here, right, we have a reaction order with respect to ammonia as being 1, and then, so first order, and then a nitrite reaction order of 1 as well, or first order. A first order plus a first order makes a what? A second order, right? First order plus a first order makes a second order, right? 1 plus 1 equals 2. So we can also find out what K is too. We can figure out what K is now with some concentrations, okay? But the rate constant is temperature dependent. Is a temperature dependent quantity, and we'll get to that in just a sec. So here's some other reactions here where it's not a 1-to-1 ratio, right? And so you get different reaction orders. It's not necessarily always related to the balanced equation, right? It's not always necessarily related to the balanced equation, but sorry, I'm getting like important emails. It's crazy. Okay. Well, we have this reaction here where we have dinitrogen pentoxide, and it decomposes down into nitrogen dioxide and oxygen right here. Right? We have a 2 here and a 4 here, but the reaction rate is still just first order, right, for that decomposition, right? Here again, we have hydrogen and iodine becoming hydrogen iodide, still first order right there too, right? And then this one right here, right, looks like it's all 1-to-1, but we have a half order reaction order right there, right? And don't worry, we're not going to deal with half orders right now, so don't worry about that. We're only going to be doing 0th, first, and second order. But it's just up here to show you that you can have all kinds of different reaction orders based on many things. One of them is being the coefficients, as I showed you in that previous, when we were going back over that little a, big A plus little b plus little b, that thing right there. So anyway, the reaction order is absolutely dependent on the rate you get when you actually do the experiment itself. Okay, and it's not always going to be the same as the coefficients. All right, so what is the relative value of K then? Well, the rate constant, K is the rate constant, right? And it's often used to determine the relative reaction. So when you have a rate constant that's on the order of 10 to the ninth, which is a super big number, right, or higher, the reaction is very fast, right? And then for reactions that are below 10 to the ninth, those are slower reactions. And so a lot of the reactions we talk about in like your body, like enzymes and stuff like that are doing your metabolism and all that stuff, doing electron transport and TCA and all that stuff, right? That's all, and all the ones that are in there that are enzyme catalyzed work really, really fast. Okay, they work really, really fast. So let's first talk about first order reactions. Okay, here I have methyl isonitrile, and it becomes acetonitrile. They look almost exactly the same, don't they? They look almost exactly the same. Well, in this particular reaction, some rates depend only on the reactant of the first power, right? And for the first order reactions, the rate law becomes this, right? Where rate equals the rate constant, or K, times the concentration of A, right? So notice it's a first order reaction, and what is the coefficient there? It's 1, right? So the conversion of methyl isonitrile to acetonitrile is first order reaction, okay? Well, how do we come up with that kind of thing? How do we determine these kinds of things, okay? So, it's gonna get math heavy now, right? And we know that the rate equals K times the concentration, right, of A. And we also know that the rate equals the change in the concentration of A divided by the change in the time with a minus sign, right? Remember, this is called the differential rate law, right? Differential rate law. We can then make it so that K times A here is equal to the differential rate law. Does that make sense? Okay. So basically what you have here is you have the rate law, right? Just the general rate law is equal to the differential rate law for a first order reaction. Okay. You can then rearrange this a little bit, right? So you can get the K, the constant, and the temperature by itself, right? You can rearrange this a little bit to do that, right? It's easy to do that if you need to know, right? All you have to do is multiply both sides by by the change in time, right? Did everybody see that? Do you want me to show you? If you multiply both sides by the change in time, like that, right? What you end up with is K minus K. Actually, let me do that again. Let's say we multiply both sides by the negative change in time, actually. Okay. And so that makes it so that you have negative K times the change in time equals the change in A So we've gotten rid of this because we canceled that out, right? And we get rid of those minus signs because we canceled those out because two minuses make a positive, right? And then let's see here. Oh, I forgot this part right here. Let me write this in again. Negative K change in time. There we go. Okay, so that's what it looks like when you multiply both sides by negative change in time, right? And then all you have to do now is divide both sides by the concentration of A. Dang, that's tiny. I'm just going to write that again. Let me erase that and write that again. That's really tiny. I can't even get my finger in there. My pen in there. I mean, it's a good thing I'm not using my finger. That would be worse. Yeah, 1 second. Hold on 1 second. I'm gonna write it bigger on the screen. Actually, I get messed up on the chalkboard, so I'm just gonna write it on the screen. Where's my mouse at? I can't even find my mouse. Oh, there it is. Do not keep this stuff, and then go back to this. There we go. Okay, so let's do that again. I apologize for that. The first thing we have to do is multiply both sides. Damn it. I always forget to make it bright. Pen. There we go. So the first thing we do is we multiply both sides, right, by negative change in t. Yes, over 1. Well, negative change in t is the same thing as saying negative change in t over 1, right? So because the numerator is just a regular number. Okay, so that does two things. We cancel out the negative change in time there with the negative change in time here, right? And then it also multiplies to this here, okay? So now what we have when we get that done is we get the negative change in time over here, right? And then K concentration A equals just the change in the concentration of A, right? Everybody got that so far? Okay. And then all you have to do now is divide both sides by the concentration of A. And the concentration of A, like that, right? So that actually cancels out this, like that, right? And that's what we get to here. That's what we have here. You see how this now looks like this? Anybody confused? Right? I'm getting there. I'm getting there. Okay, so we cancel that out, and now we get this equation here, right? And now we have to do an integral. Okay, does anybody remember how to do an integral? So when we get this here, right, we need to integrate this by taking the natural log of this, right? But there's a special little rule, if you remember from calculus, called the natural log the natural log quotient rule, where it says that anything that's ln, right, ln x divided by y, whoops, x divided by y, right, like that, equals ln x plus ln y. Okay, that's called the oh, sorry, not plus, minus ln y, right? That's called the quotient law, right? The quotient rule for logarithms. Okay, and so the reason why usually you see it as lowercase ln like this, right? But when you look on your calculator, it's an uppercase ln. That's why I put it as uppercase for you, right? That also does look like IN too. So that's why I wrote it out as big L. So when you get that right there, right? All that really means is that you can take this entire term right here, right? And turn it into this. Turn it into that. Okay? So what you get then is when you use the quotient rule to do that natural log, the integration, right? You get this, right? That's what you get. So notice now it's the positive A, ln A here equals the negative KT plus the ln of the A, right? So that comes from the quotient law. And the reason why we even did this, or quotient rule, the reason why we did this is because this is called the integral rate law, right? This is called the integrated rate law right here. Compare that to doing the differential rate law, which is what we had up here, right? Where you had to have all this the change and stuff right here. This is called the differential rate law. Compared to that, which is the integral rate law, integrated rate law, and you can see how you can just plug things in, right? And the coolest part about doing that is that if you put y equals mx plus b here, which is the line, the equation of a line, you can see how the natural log of the concentration of A is the y-intercept, right? I'm sorry, not the y-intercept, the y value, right? The negative rate constant is the slope, right? And then the t here is the time, which is x, right? And then the y-intercept is the natural log of the initial concentration of A, right? And that has a lot of implications because that means you can graph this now, which is what you'll be doing in lab today. You can graph that now. Yeah, man. Yeah.
You said that this one is the integral rate law.
Yes. 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 Integrated rate law. I was saying you have to take the integral of it, but the law is called the integrated rate law. Yeah, no problem. Integrated rate law. See, I told you guys on Monday we're going to be doing a lot of math. So, because we've moved from the conceptual part of chemistry now to the mathematical part of chemistry, and so that's the next few chapters we have. The chemical kinetics, solution equilibria, acid-base equilibria, and thermodynamics. So we're doing a bunch of math now, right? So what that means then, right, is that it means that the plot of ln A, right, the natural log of the concentration of A versus time is linear, right? So if you were to take all your data that you took on Monday, right, and made it so you did the natural log of all that data, and you plotted it against how much time for each spot, right, for each reaction you did, not each reaction, sorry, each data point you took, right, and it comes out as a straight line, it means your reaction is first order. Does that make sense? Right? Does that make sense? All right. So in respect to the first order reactions, the plot of ln A versus time is what? And if it makes you feel any better, I'm not going to make you go through and do any kind of like derivation of the integrated rate laws like I just did on any exam. I was just showing you how we got there. Does that make sense? But I could be a real, butthole and put one on the written part of the exam. Please derive the integrated rate law from the differential rate law, right? For a first order reaction. What if I did that? Would that be bad?
Yes.
Would that be bad on the written part of the exam? Okay, so we already alluded to this before at the very beginning of this. PowerPoint, we were talking about those factors that affect the rate of reaction, meaning it makes it go faster or slows it down, and such, right? And so, of course, temperature, right, will affect the rate of reaction. And the reason why it does is because it increases the frequency of the collisions of the molecules, right? And the more times those molecules collide with each other, the more likely they'll react with each other, right? And then, of course, the orientation of the molecules. It turns out that these molecules have to be in the perfect orientation for them to be able to have their p orbitals overlap, right, to make a new compound, right? So they also have to be in the correct orientation. So if there's more collisions, there's a higher chance that the orientation of the molecules are going to be correct, right, to proceed with a reaction. And so the thing that we're going to be talking about today, right, is called the activation energy. It's the energy needed for a reaction to take place. It's called the activation energy. Okay, that's our important topic for today, activation energy. Right, activation energy. Remember that phrase. Okay, remember that phrase. So let me see here. I didn't even log into my thing yet. So talking about temperature, right? Talking about temperature. Uh, Generally, as temperature increases, the rate increases, which makes sense, right? Uh, because I just said if you increase the temperature, you increase the frequency of those collisions between the molecules, and the more you increase the frequency of collisions, the more likely that the molecules will collide with each other, and then also more likely that the molecules will collide each other in the correct orientation to cause a reaction to occur, right? And so what you're seeing there on the right-hand side is actually a picture of a glow stick, one in hot water, one in cold water, right? And glow sticks, when you break them, there's two chemicals that mix together and they fluoresce very, very brightly, right? They fluoresce really brightly, or glow, if you want. That's why they're called glow sticks. Um, but when it's in cold temperature or cold water, right, the glow isn't as bright. But when it's in hot water, the temperature is much, much brighter. And so that's just an example of how heating something up will increase the reaction. And this happens a lot, especially in organic chemistry. I was telling you a little while back how when you do an organic reaction, you can use this thing called a reflux. And in a reflux, quite literally, what happens is that it was that story I told you where I had the reflux going overnight and the hose popped off and then the water went everywhere and it flooded the third floor. Yeah, maybe I told that to a different class. I don't know, but that was a pretty bad situation anyway. Um, but anyway, so in a reflux reaction, you have your reaction mixture, and it's like bubbling, right? You have your reaction mixture, and it's bubbling, and what happens is that the reaction mixture will start to evaporate. But then we have this thing on top of it called a condenser, and it keeps all the vapor inside, so that you can keep on doing the reaction. Keep on doing the reaction while it's still hot. Sorry, I got to put in my freaking code here for getting into Wesleyan again. It's like they don't know I work here. 379376. There we go. Yes, stay signed in. It never works, but stay signed in anyway. Um, and it also says here, do not reveal this code to anyone. So I guess I should have kept my mouth shut when I did that. Anyway, so the rate is constant. Sorry, the rate constant is temperature dependent. It increases as temperature increases. The rate constant doubles with approximately every 10 degrees Celsius rise. Right. So here's a reaction where we have I forgot what it was called, but I remember that's acetonitrile. So whatever it is that becomes acetonitrile, right? the As the temperature increases, you can see how fast the rate rises, right? How fast it rises. So the hotter it gets, the better it is for a reaction. Okay, the hotter it is, the better it gets for a reaction. So let's talk more closely about the frequency of reactions, or sorry, the frequency of collisions, right? So there's this thing called collision theory, right, or collision model, and that states that molecules must collide to react, right? It's based on the kinetic molecular theory. If you guys remember, the kinetic molecular theory was the kinetic molecular theory of gases. Remember that? And in the kinetic molecular theory of gases, it said that molecules were of gas are very far apart, and they bounce around inside their container in random but straight directions, right, until they collide with each other, and that's what causes pressure. Do you remember that, the kinetic gas theory? You can always look that up later. It's not as important as doing the collision model, right? Molecules must collide to react. If there are more collisions, more reactions can occur. So if there are more molecules, the reaction rate is even faster, right? So that's just based on the the 0th order, 1st order, and 2nd order type of reactions, right? Because if there are more molecules, the reaction is faster, right? So that's like a 2nd order reaction where if you double the amount of molecules, you get the double the rate, right? And it gets even faster if you heat it up. In a chemical reaction, bonds are broken, and new ones are formed. So molecules can only react if they collide with each other. So that's like 5 different ways now I've said they have to collide with each other, right, to react. Okay, so wrong computer. So the orientation of molecules. Okay, molecules can often collide without forming products. Aligning molecules properly can lead to a chemical reaction. The bonds must be broken and made, and the atoms need to be in proper positions. So here, excuse me, here we have green is usually chlorine, all right? And so here's a chlorine molecule about to collide with another molecule that may have a chlorine there too, right? And if it's going to hit the chlorine model in on, and we already know chlorine likes to be with itself, right? Because it's one of those diatomics. Remember that? So chlorine already likes to be with itself, okay? And so this chlorine atom collides with this chlorine atom right here that's attached to this. So reaction occurs. A new bond forms to make the chlorine diatomic molecule, right? Chlorine gas, and then the rest of this stuff flies away, right? But the problem is that if you had a collision where the chlorine molecule is not faced so that the chlorine atom collides with it, then this chlorine atom will just collide with, let's say, usually red is oxygen, right? So it collides with this oxygen, right? And it just bounces off, and there's no reaction at all, right? So the more collisions there are, the more likely that you have the orientation, the molecules in the right orientation. So you get a chemical reaction where uh, chlorine gas is released, right? And then you have this leftover product right here. But you also have some that, it collides incorrectly, you have no reaction happen at all. Okay, so both of those are super, super important um, for a reaction to occur. So your first question for today is this: which of the following does not happen during chemical reaction? Molecules avoid each other, bonds are broken, new bonds are formed, or all these happen during a chemical reaction? Let's see here. So far, I only got 2 responses, 3 responses. 4 responses. 6 responses. How many people are here today? 10? Yes, 10. So we need 4 more people to respond. Read this question carefully here, okay? Which of the following does not happen during chemical reaction? Molecules avoid each other, bonds are broken, new bonds are formed. Got 7. We're waiting for 3 more people. 8, 9. One more person. 10. Okay, good job. Good job. All right, so the vast majority of you picked A, which is correct, right? Uh, it's definitely not C. Well, it can be C because C is one of the things that does happen in the chemical reaction, but it can definitely not be D, right? Because you look at this answer right here, if you look at these questions and this answer, right? Bonds are broken, so that's correct. B is correct. New bonds are formed, that is also correct, right? But what did I just harp on for like 5 minutes just a second ago? Yes, molecules must collide for a reaction to occur, right? Molecules must collide for a reaction to occur, but that says molecules avoid each other, right? So make sure you're reading these things carefully and you're listening to what I'm saying, right? Especially those people who picked all of the above, okay? I'm not saying these things 5, 6 times so that, for my health, all right? So make sure you're listening and you are reading the question carefully, okay? All right, so continuing on. The minimum energy needed for a reaction to take place is called the activation energy, right? An energy barrier must be overcome for a reaction to take place, much like a ball must be hit to overcome the barrier in the figure below. So here we are, a golfer is playing some golf, you know, and he's going to follow. Well, I guess he's not following through because he's just putting right now, but he's got to go over this hump here, right? And this hump here is like an activation energy, the energy required to make a reaction happen. The problem with this picture, though, is that it's not very accurate, right? It's not very accurate because the land over here, the level of the land over here, and the level of the land over here is the same, right? Generally, what happens in an activation energy is that, and the reason why reactions occur to begin with, is because you have a molecule and it's already at this certain energy, right? It wants to turn into something else, so it goes over the activation energy, right? But the reason why it wants to do that is because going over the activation energy to become this new molecule is lower in energy than being the way it was originally, okay? So there's got to be some kind of energy benefit during this reaction, right? There's got to be some kind of energy benefit. And many times, right, molecules become other molecules because the product is less energy, right? It's more stable. And this is quite true with our example with salt, right? With sodium and chloride. Remember that chlorine gas by itself can kill people, very, very deadly. And then sodium metal is also very explosive, right? But we put them together, and none of those things are true anymore about those two combination, right? Now they're on top of your popcorn, right? Or I used it to season my steak yesterday, right? So the salt molecule, sodium chloride, is far less energy, far more stable than both the chlorine atom or chlorine molecule, gas molecule, and the sodium molecule or sodium metal, right? If they were separate. Does that make sense? Right? That's what activation energy is. So there's this thing called the transition state. Okay, there's this thing called the transition state, and it's exactly what it sounds like. Where are you going? Oh, okay. I got so sad. I was like, I thought this was a riveting lecture. Anyway, so transition state. So, and when you're talking about transition state, the transition state is that part of the activation energy at the very top when the molecule is changing to the new molecule, right? So it's quite literally what it sounds like. It's transitioning. It's the state in which the molecule is transitioning, right? Reactants gain energy as the reaction proceeds until particles reach the maximum energy state. The organization of the atoms at the highest energy state is called the transition state, or the activated complex. The energy needed to form this state is called the activation energy, right? So just remember that the transition state is the state in which the molecule is becoming the new molecule in the reaction, okay? So here's what it all looks like when we take it off of the golf course, right, and actually use some chemistry graph, right? Because we use a lot of graphs in chemistry, I know, right? So here is a plot called the reaction progress plot. Okay? On the left-hand side, on the y-axis, we have a potential energy. on the x-axis, we have the reaction progress. That means how much time is passing by, right, as the reaction is proceeding, okay? And so here we have that molecule that I can't remember what its original name is, right? Isonitrile something or other, I can't remember. Methyl isonitrile, who knows? But it's becoming acetonitrile over here, okay? And notice what I said before, right? Remember we had the golf course where the thing was flat on both sides of the hill, but in real life, an activation energy usually has its product lower in energy. See, you see how the acetonitrile right here is lower in energy than its original reactant, right? So, I mean, what's the point of a molecule becoming another molecule if it's not beneficial to it, right? And for most molecules, just like most people, stability is what they want, right? A stable relationship, stable emotions, stable finances, right? That kind of stable job. Molecules just want stable energy, right? They want stable energy. And so there's no reason for a molecule to go through this heat activated activation energy thing, go through all this trouble right here just to become acetonitrile if it wasn't going to be beneficial to it, right? So we start here. This is the reactant, right? And the reaction begins, and then this part right here, the energy between the products, sorry, the reactant's energy and the energy required to get to the activated complex, or also known as the transition state, right? It's called the activation energy, right? So this is the energy between the reactant and the energy needed to get to the transition state. That's called the activation energy right there. And you always know there's you always know that there's a transition state, for one thing, because it's always at a peak of one of these things. But then also when you look at the molecule up there, you see how the CN right here, the cyano group, or the also known as the cyanide group, right, is starting to bend, right, as it goes up this hill, and then it starts to rotate. And when it's rotating, you see that there's no bond there anymore. What do you see there? You see 3 dots, right? Those 3 dots means that it's going through transition, it's changing, right? It's going through transition and changing, flipping around, and as soon as it flips around, right, and becomes the acetonitrile, it's so much more happy, and it's a downhill turn now, right? It's just going downhill to become acetonitrile, which is way less energy than the original reactant. So the other thing you need to know from this plot is that the energy between the reactant and the product, which is this orange one right here, is the change in energy, right? And there better be a change in energy that's beneficial to that product, right? Or it's not going to happen. This reaction won't happen, right? Imagine if, for example, if acetonitrile wasn't way down here, but its product was up here, right, in energy, would that reaction proceed? No, because now the product is more energy than the reactant is, right? So since it's lower in energy here, it wants to go down there. It wants to go through and get more stable, switch things around. It's kind of like getting a new job, right? You know, so it's this molecule's original job was just so unstable, you know. It didn't have any like, oh, that's actually a good example would be me. So when I was a forensic scientist, I was actually doing adjuncting, like part-time teaching at the same time, right? But that wasn't very stable. Like it was based on semester per semester. If the school needed me to teach, right, then I would teach. But if they didn't need me to teach, then I wouldn't teach, and I wouldn't have a teaching position that semester. So that was a very unstable position, right? But then Wesleyan called up and was like, hey, we'll give you a full-time position where you can teach all the time. No worries about not having a class to teach one semester or not, right? That's a more stable job. So I left the adjunct job, the part-time teaching job, right, and came here because it's a more stable job, right? It's the same thing with molecules. They're leaving a worse situation over here and becoming a quite better situation here, right, on the other side. There's no reason to go through all that work, right? If you're not going to be in a better situation. What happened? Which one right here? This line right here? The dotted line? Oh yeah. The red line? Which one? Yeah, that's what I'm talking about. This energy is lower than this energy. That's why this molecule wants to become acetonitrile, right? right? If a job, as an analogy doesn't work, think about it being like maybe a volatile relationship, right? And you're like, man, this relationship was super fun at the beginning, right? Because it's so crazy, right? And then you're like, okay, I need to get a new girlfriend or something because I don't know, I need more stability in my life. I'm a homebody, and so you break up with your girlfriend, and then actually it's probably the opposite. My girlfriend would do that to me. So anyway, because I used to be super crazy. Anyway, she'd break up with me, and then she'd find a more stable boyfriend, right? And that'd be her now. Less energy, right? They wouldn't have as much fun, right? My girlfriend and her new boyfriend, but at least it's not as crazy in their relationship. Okay, your next question. Which of the following is true about the reaction process? At the lowest energy state, the transition state is formed. The reaction can only be exothermic after the transition state. The rate constant depends on the magnitude of the activation energy, right? Or none of these statements are true. Okay, which question was this one on the Microsoft forums? Since I wrote these so long ago, there's like a whole bunch of other classes in between, so I have to find it. Reaction progress. I bet you that's it. There it goes. Got 4 more people. I didn't outrightly state this yet, so I'm seeing you guys can make some connections here between the last few lectures and this. 2 more people? 1 more person? Still waiting for that 1 person? There we go. Wow, there was an answer for every one of them. That's crazy. But that's okay. I didn't outrightly say this, so I just wanted to see how this was going to go. The vast majority of you picked C, which is correct, right? C is correct. We know already, right, that, let me switch back to the laptop. We know already that the highest energy state is actually where the transition is, okay? We also know, so that's incorrect. We also know that a reaction doesn't have to be exothermic all the time, right? It can also be what? Endothermic. So that's incorrect. But this one right here, rate constant depends on the magnitude of the activation energy. That makes sense, right? If the activation energy is lower, then the rate constant doesn't need to be as high, right? The speed can be faster. Does that make sense? Right? I did not rightly say that, but I was hoping you would make that connection, which most of you did. I'm very proud. Good job. Okay. So, starting to run out of energy already. Where's my activation energy at? Distribution of energy of molecules. So the 2 things that you need to know from this slide, or these 2 lines right here, gases have an average temperature, but each individual molecule has its own energy, right? At higher energies, more molecules possess the energy needed for a reaction to occur, right? So this is the thing I was telling you about before, where you have like a puddle of water on the ground, right? And it's just regular room temperature. If you just leave that water on the ground, eventually it would all dry up, right? Because some of those molecules have the energy, enough energy for it to evaporate, but most of them don't, right? So it just takes some time, a lot of time, right? But if you heated up the water, right? If you had like a heated floor, right, and you heated up that puddle, what would happen? The water would evaporate faster, correct? It's the same thing here, right? Same thing here. Most gases have just average temperature at room temperature, right? But some of them do have enough to actually do a reaction, right? But if you want more of them to have enough energy to do the reaction, you just heat it up, give it more energy. And we're using energy and heat synonymously here, okay? Like heating things up is the same thing in this case as increasing the energy, okay? So this is the one equation you need to know from this set of slides, okay? And I'm not going to try to derive it for you or anything like that. Don't worry. I know that was a little bit rough last time we did that, but Arrhenius. So funny thing about Arrhenius, right? Arrhenius didn't just come up with an acid-base theory, but he also came up with this equation here, right? Arrhenius noted the relationship between the activation energy and temperature, right? And so notice right here, we have the ideal gas constant and temperature right here, right? And we have the K here. You can solve for the activation energy, right? The activation energy also can be determined graphically by reorganizing the equation like this, right? Where this looks just like a y equals mx plus b equation, right? This is y equals mx plus b. So you can actually graph it too, the same way we did with the second order, the zeroth, first, and second order reactions, right? And then you can also rearrange the equation again, right? If you have both rate constants and you have the temperature you began at and the temperature you ended at, right? Then you can also solve for activation energy there too. So this is the only equation you need to know for this part of the thing. So when you graph, right? When you graph using that linear line, the line I just showed you, the y equals mx plus b equation I just showed you for activation energy, right? Where we have 1 over the temperature, right, on the x-axis, and then we have ln of the rate constant on the y-axis. The slope, right, is equal to the negative activation energy over the ideal gas constant, right? Which is great because all you have to do now is solve for EA. All you have to do is solve for EA, and you have the activation energy, right? So really, what this is even saying here is that the change in Y is the activation energy. Does it make sense? Right? Because the slope is what? Rise over run, right? And EA is equal to negative EA is equal to what? The rise or the change in Y, right? And so the activation energy is literally just the top number of a slope. Okay? Good stuff. Good stuff. So law versus theory, okay? Law versus theory. And this is in reference not to science in general, but in reference to kinetics, okay? Kinetics gives us what happens. We call that the rate law, right? For example, what happens when you add in twice as much concentration of reactant? The reaction rate doubles, right? Whereas theory is different, right? Why do we observe the rate law? We use it to explain a theory, and the way we do that is called the mechanism. And I was telling you that before, where in organic chemistry, you'll have to go through and do some very detailed mechanisms on how bonds break and how bonds form, where electrons go, and all this stuff, right? To do a mechanism, right? But using the rate law, you can figure out some of the different mechanisms, right? A mechanism is a series of stepwise reactions that show how reactants become products. We won't be doing any of that here, right? But just be prepared for that kind of thing. Okay? Reactions may occur all at once or through several discrete steps, right? And each of these processes is known as an elementary reaction or elementary process, okay? Elementary reaction or elementary process, okay? All right, so this is your next question. Kinetics gives us what happens, which we call the description of the what? Okay, so let's see here. Forms, rate reactions, rate constant. No, not rate constant. Rate, oh, here it is. Here it is. Got 5 answers so far. Nine answers so far. Just one more person. Un persona? Yes, there we go. One person. Okay. All right. So, again, most of you got that one right. I am very appreciative. The answer is, in fact, B, right? I just said right before the question, the rate law tells you what happens, right? The rate law tells you what happens. And the question was, in kinetics, what happens, which is called, kinetics gives us what happens, which is called the what? It's called the rate law, right? It's not the theory, it's not the mechanism, but it's the rate law, okay? So that might be a definition that you see on a multiple choice question on an exam, right? All right, so there's this other thing called molecularity, right? Molecularity. And so it's actually you get this in organic chemistry too, but it's pretty self-explanatory. So molecularity is just like applying a word to the number of molecules involved in the reaction, right? So, for example, here is we have unimolecular reaction is just one reactant, right? Uni meaning one reactant. Bimolecular reactions, right? Both of these are bimolecular because you have A plus A makes something, right? So that's two molecules, or A plus B makes, is two molecules. So that's why it's bimolecular, like bicycle, two things. And so an A plus A would be like two chlorines getting together, you know? Whereas an A plus B would be like a chlorine and a sodium getting together, right? Both of those still involve two different molecules, right? Or two different reactants, rather, okay? Termolecular, right? That comes from the Greek tertiary, which means three, right? And so three here, so this is three of them getting together. So this is like making an ozone, right? Three different oxygen atoms getting together to make ozone, O3, right? So that's three different reactants. Here we have two of the same reactants plus a different reactant, right? That's also termolecular. And then we have here termolecular is three different reactants. So the thing that I want you to notice about this, though, is that there is a rate law associated with each one of these, right? So, for example, one in a unimolecular reactant, right? Unimolecular reaction, not reactant, but reactant, right? The rate is equal to A, just A by itself, right? So that's a first order reaction right there, okay? Which makes sense, right? You double A, you get the reaction rate doubles, right? Bimolecular reactions, right? The rate is second order, right? Which means it quadruples every time you double the rate, the reactants, which makes sense because you have double the reactants in there already, right? They're the same reactant, okay? The other bimolecular is A plus B. So here, it's going to be the rate constant plus the rate constant of A plus the rate constant of B, right? Overall, this is overall this is a second order reaction, but on its own, they're first order reactions, okay? Here, this is the first time you've seen this before. This is a third order reaction, right? It's a third order reaction right there, okay? So A plus A gives you the rate equals the constant times the concentration A to the third, right? And then here, A plus B gives you an overall, right? An overall third rate equation, right? I don't know what, I think that's a typo. There shouldn't be a plus sign there. So in your notes, you should cross out that plus sign between on the bimolecular, because if you put a plus sign in there, when I ask you a question, it's going to be wrong. So get rid of that plus sign. That's a typo. Yeah, there shouldn't be a plus sign there. I'm surprised Mary didn't catch it. What's that plus? What's that plus sign for? Anyway, back to the termoleculars, right? The termoleculars, right, all have uh, uh, third order reactions, right? Because there's three reactants, number one. But notice also here for the termolecular that has the two of the same and one different, overall it's a third order reaction. And then here, A plus B plus C is also a third order reaction overall, right? Them individually, with respect to each other individually, they're first order, right? But altogether, they're overall they're third order reactions. So you could say then that the unimolecular tells you what the overall reaction rate is, right? The overall reaction rate for unimolecular is what? 1, or first. The overall for bimoleculars is 2, right? Or second order. And the overall reaction order for termoleculars are what? Third order. Make sense? Right? The molecularity of an elementary reaction tells us how many molecules are involved in that step of the reaction mechanism, which is what I've been saying the whole time. So let's talk a little bit about the termoleculars, right? Termolecular steps require 3 molecules to simultaneously collide. I feel like my tongue is colliding. Simultaneously collide with the proper orientation for proper energy. These are rare. If they indeed do occur. These must be slower than unimolecular or bimolecular steps. Nearly all reaction mechanisms use only unimolecular or biomolecular reactions, not biomolecular, bimolecular, right? And that's why when we went through kinetics the last couple of days, we only did like, 0th order, first order, and second order, right? Because you very rarely get the third order reactions, right? Okay, you very rarely, so let me rephrase that. You very rarely get the termolecular reactions, okay? All right, so let's talk about the limits of the rate. What limits the rate, right? The overall reaction cannot occur faster than the slowest part of the reaction mechanism, right? So it's basically like a bottleneck, right? In the reaction mechanism, there'll be a step that's a bottleneck, right? And we call that the rate limiting step, okay? Because the rate can't get any faster than that bottleneck, okay? That's called the rate limiting step, right? So here in this picture right here, which I haven't actually seen yet, so let me study it real quick, right? So cars are slowed down at toll plaza A, right? And so that's the rate determining step, right? In the passage through through A, because since they're being bottlenecked right there, or slowed down right there, right? They're going to be slow getting into toll plaza B, right? Whereas if the cars are slowed at toll plaza B, the rate determining step is going to be at toll plaza B, right? So it really is like a bottleneck. You can't go any faster than in the reaction if there's a step that slows everything down, okay? So what then is required? What then is required of a plausible mechanism, right? What do we need to have a plausible mechanism for a reaction? Well, the first thing is that the rate law must be able to be devised from the rate determining step, right? So what that means is that your rate law will not be based on any of the faster steps of the reaction. It's always going to be it's going to always be based on the rate limiting step, the slowest step of the reaction, okay? The stoichiometry must be obtained when all steps are added up, all right? And then, of course, the stoichiometry is the coefficients of the reaction, right? They all got to balance. Each step must balance. I just said that. Each step must balance, just like any other equation, right? And the intermediates are made up and used up, right? So whenever you have a reactant, right? For example, you have 2 chlorine atoms as reactants. They do their reaction to each other, right? And they become chlorine gas on the other side of the activation energy, right? There's no more chlorine left over. Everything has to be used up. Does that make sense? Right? Okay, so that's an important step there. Contrast this with this here, which is a catalyst. A catalyst can be used to increase the rate of reaction, lower the activation energy, right? But once you're done with the catalyst, like nothing else matters anymore, because the catalyst is just, you can just take it out and it'll be the same, right? So the important thing about a catalyst is that a catalyst can be used in a reaction, but it's not a part of the reaction equation, right? Not a part of the reaction equation. Okay, catalyst. All right, catalyst. This is more important. This is what I think is more important. Catalysts increase the rate of reaction by decreasing the activation energy of the reaction, which I said that before, right? Catalysts change the mechanism by the process by which it occurs. So here's our reaction diagram again, our reaction energy diagram again, and our normal reaction with hydrogen peroxide here, right? Becoming water and oxygen, right? It's got this super high activation energy, But again, this is an exothermic process. So when it gets down here, it's actually lower energy because obviously water and oxygen are lower energy than hydrogen peroxide. But when you have an enzyme in there, right, or an enzyme or a catalyst or something in there, it can actually make the reaction go much faster, right, because it lowers the activation energy. Okay, it lowers the activation energy. So um, I think if you look right here, you can see that there's a Br right there, right, a bromine right there, and the bromine doesn't really do anything but act as a catalyst because you get two bromines there, two Br minuses there, right, and you get two Br minuses out, right, but then the reactants change, right? You had two hydrogen peroxides and you had some protons, but uh, now you have two waters and two oxygens, right? So the Br and the two proteins are the catalyst, right? And the H2O2, the hydrogen peroxide, is the reactant, and the products are water uh, and O2. So oxygen. So what I want you to be able to do from a reaction diagram like this is just look and see which is the products, right? Which is the product. Here it's hydrogen peroxide. Which is the reactants? Here it's hydrogen peroxide. Which are the products? Water and oxygen. And then which is the catalyst, right? And the catalyst here, the thing that doesn't change, but is there to help the reaction go a little faster, is the Br and the hydrogen, right? So be able to look at these reaction diagrams and tell the difference between a catalyst, a product, and a reactant. All right, so there are three types of catalysts. There's a homogeneous catalyst, there's a heterogeneous catalyst, and there's an enzyme, right? Enzymes are biological catalysts. That's what I studied when I was in grad school. I studied a bunch of enzymes. There's a whole thing called enzymology, right? So in a homogeneous catalyst, the reactants and the catalyst are in the same phase. Many times the reactants and catalysts are dissolved in the same solvent as seen below, right? So a homogeneous enzyme would be like both the catalysts are liquids, right? Or they're dissolved into the liquid or something like that, where you can't even really see after you've added the catalyst that the catalyst is there. Okay, so that's a homogeneous catalyst. It makes sense because homogeneous means the same, right? And then this is the reaction I was talking about before, right? When I was talking about the hydrogenation of fats, okay? That's a heterogeneous catalyst because the catalyst here is this platinum metal, right? This platinum metal right here, okay? And then the reactants are actually going to be the hydrogen molecule there and the hydrocarbon, like a fat, right? And when you have this heterogeneous catalyst, the platinum stays platinum. It's still a metal, a solid, right? But the gas is still gas too. So they're not the same phase, right? In the homogeneous catalysts, they're the same phase. But in the heterogeneous catalysts are not the same phase, right? We have a gas here, we have a solid here, right? And so the catalyst will help the two molecules get closer to each other, and then the platinum will add the hydrogens to the molecule, right, making a new molecule. So that's the same thing I was talking about before with the double bonds in a vegetable oil, right? It'll add hydrogens to the double bonds of the vegetable oil, and the way it does it is by using a catalyst like that, right? So that's called a heterogeneous catalyst, okay? So the thing I need you to remember about that is heterogeneous catalysts are different phase, whereas homogeneous catalysts are normally the same phase. Okay. So you don't have to scan this. We'll just talk about it real quick. Which of the following is not true of a heterogeneous catalyst? The reactant and the catalyst are dissolved in the same phase. That's definitely the one that's not true. The catalyst is a different phase than the reactants. That's true. Absorption of the reactants is often the rate limiting step. That's also true. So A is the answer there, right? Because reactants and catalysts dissolved in the same phase is usually what? The homogeneous catalyst, right? It's usually the homogeneous catalyst. And then we're heading to the pretty much the end now here, right? Enzymes, which are my specialty, are biological catalysts, right? You wouldn't be alive if there weren't enzymes in your body because the vast majority of the reactions that happen in your body right now, like in metabolism, like the TCA cycle, glycolysis, the electron transport chain, amino acid stuff, the DNA replication, all those happen by enzymes, okay? And how it does it is that the enzyme will actually create this little microenvironment, what it's called the active site, right? And then the reactants go into this active site, and the enzyme like forces the reaction to occur. Okay, It forces the reaction to occur. So when you have reactants in an enzyme reaction, they're actually called substrates. That's important. So remember that. Reactants in a biological catalyst or an enzyme are called substrates. So you always have the enzyme and the substrate, right? And then, so the substrate is like the molecule, and the big enzyme comes over and grabs onto it like this. That's called the enzyme substrate catalyst, right? I mean, enzyme substrate complex. And that's what forces a reaction to happen that would normally not happen. So a really good example of this is beef liver. It's got this enzyme in it called catalase. You'll find that every enzyme ends in ase, right? Catalase. And catalase will actually, this inside beef liver, will turn hydrogen peroxide into water and oxygen, right? Which is actually the exact same reaction we saw previously here. Here, with the bromine, excuse me, with the bromide ions and the protons, right? Which is basically hydrogen bromide, right? Hydrogen bromide, or hydrobromic acid, or hydrogen bromide gas, right? It's the same thing as that, right? But we don't want to use acid. If you use an enzyme called catalase, it will do the same thing. It will do the same thing. It will turn the hydrogen peroxide into water and oxygen, right? And then the catalase can still be reused again, right? It can still be reused again. This is actually, if you go to biochemistry, like the next class, not the next class is organic. The class after that is biochemistry. I think you actually do a reaction with this because um, the biochemistry professor was actually looking for beef liver the other day. So I think they're actually doing it now. It's actually a lot of fun too. Good old catalase. And then this is the last slide here. So I was talking to you before about how we have substrates and enzymes. Enzymes are actually mother huge. They're really big things, right? They're very large molecules. They're made of proteins, and well, let me rephrase. Enzymes are proteins, and they're made of amino acids, which you'll learn about that later on in life, right? But they're huge molecules, and they have this little thing in there, this little spot in there, right, called the active site. And the active site, for, this is very simplistic, but it has a place that's perfectly suited for the substrate to enter, right? And when the substrate, remember the substrate are those reactants, right? The substrates are the reactants. When those substrates or the substrate enters the active site, the enzyme will conform it and move it around and change it so that the environment around it will make it so that the substrate is more likely to react and become something else. And that's called the enzyme substrate complex. So after it's done doing its reaction, the enzyme will let go of the products, right? These are the two products now, it just lets it go. And then all you're left with is the enzyme. And notice that the enzyme remains unchanged throughout this reaction, but the substrate changed to these two things as the product, right? So in the enzyme substrate model, the substrate fits into the active site of an enzyme, which is much like a key that fits into a lock, and they're very specific. So this is very simplistic in what it's saying because in real life, it's not exactly lock and key like this. In fact, the enzyme is a very dynamic molecule, and the substrate, when it gets close to the enzyme starts to fold around it. Like it will actually be dynamic and move around it and stuff like that. So it's not just as simple as lock and key. There's a lot of movement happening to actually make it happen. Okay. All right. So I do want you to answer this last question though. So scan this just to make sure, just so I know that you guys got done with all this right here. Which statement is true about enzymes? They are biological catalysts. They have a region called the active site. They are specific, or all these statements are true. All right. Well, see, it's a good thing that you're here to scan this now because then I can count you to be here today. Are you in? Is everybody signed answered? I don't want to have to log into the computer, so that's why. I want to see who actually stayed for discussion after I said you have to stay here the whole time. compared to who is still in class, which most of you are here, so I'm very proud. I'm very happy about that. Everybody signed in? Yeah, good, right? All right. So what is the answer here? It's going to be D, right? They're all these statements are true. In fact, enzymes are biological catalysts, right? They have a region called the active site where the reactants attach. What are the reactants called when you're using an enzyme? Substrate, exactly. They're called the substrate, and they're super specific, right? And then all those statements are true.